Hello everyone, I hope you're all doing well. In this video, we'll be solving problem 3 from chapter 4 of Introduction to Statistical Mechanics by Roger Bowley. Let's see the problem statement and we'll dive directly into the solution. And if you are wondering that where are the solutions to other problems from the similar chapter or from different chapter from this book or from different book on statistical mechanics or whatever book you are looking for, you can find it on my channel. So just put your queries in the comment section. I'll direct you to your desired video as quickly as possible, within an hour or so, because I'm really quick at responding to comments. I love comments. So let's see the problem statement here. Here's a statement. It says that if 10 to the power minus 7 joule of heat is added to a system which is so large that its temperature doesn't change, by what factor will the number of accessible states of the system increase if the temperature is 30 Kelvin? Okay, so we have a single system here and this amount of heat has been added to that system. Okay, we are considering here a single system, so it will be related to the entropy of a single system. So the key things that are given here is the heat that is being added, 10 to the power minus 7 joule, the temperature 30 Kelvin, the constant temperature, keep that in mind, and we have to calculate by what factor will the number of accessible states of the system increase. So let's quickly jump into the solution. We'll first write the data. So in our data, we are given with the heat added to the system, which is, let's say, Q, that is equals to 10 to the power minus 7 joule. And we are happy that it's already in SI units. Okay, otherwise we have to convert it first in the data section. The temperature of the body is constant and it is 30 Kelvin. Other than that, what we need to calculate is by what factors the number of accessible states increases. So that is actually this ratio that we find in the formula for entropy. Okay, we'll see it occurring here. So you can write in descriptive form here, factor by which number of accessible states increases, that is equals to WF by WI, that is equals to question mark. That is something that we need to calculate. So it's up to you. That description will add details to your solution. Now let's do the calculation part. You need to use a black or a blue marker. I'm using brown because it matches with my desk. So let's see that we know that entropy is given by Boltzmann relation, or you can say according to the Boltzmann's definition of entropy. I don't know what I have written here. We know that entropy is given by Boltzmann definition of entropy. We know that according to Boltzmann definition of entropy, okay, that's a better wording, that entropy equals Kb natural log of Wf by Wi. Okay, that's the Boltzmann definition, and let us call it as equation number 1. We also know that in thermodynamics that entropy is given by S equals Q over T when T is constant. Okay, so we can equate both of these equations because we want Wf by Wi and we know Kb, Q and T, but we need to calculate this thing, so we can equate both of these equations. So putting 1 into 2, or you can say equating 1 and 2. So after putting 1 into 2, we'll place the value of S here. So it's Kb natural log of Wf by Wi, that is equals to Q over T. We can take Kb right in this side of the equation so that we can separate Wf by Wi. So it's Q by Kb T. Kb is Boltzmann constant. And now we need to remove that natural logarithm here. So for that purpose, what I'm going to do is to make natural logarithm here. So we know that in rough work, I'll say that natural log of E is equals to 1. You can write it like since you can write here like that. Since natural log of e equals 1 and 1 is everywhere, so we can write 1 here being multiplied by q by kbt. In next step, I'm going to write natural log of e instead of 1 because natural log of e is equals to 1. These are some minor details that matters a lot, and these details actually confuses students when they don't know about it. So natural log of wf by wi, and that's the property of natural logarithms, that its coefficient becomes its power. Okay, so we can move its coefficient on the power of this term of which natural logarithm we are taking. So natural log of e to the power q by t kbt. Okay, and now we have natural logarithm on both sides, we can cancel it out, and wf by wi equals e to the power q by kbt. Alright, so let's quickly put the values of q, kb, t right into this equation to get the value of wf by wi, and we'll solve the exponent first, like this term in the exponent, and we'll see what it comes out to be. Q is 10 to the power minus 7 divided by kb is 1.38 multiplied 10 to the power minus 23, and t is 30. So let me use a calculator and I'll get back to you people. I'm back, everyone. If you are, it is e to the power 2.4 multiplied 10 to the power 14. Okay, so that is the factor by which number of accessible states increases. You cannot calculate this value using calculator because it becomes infinity, or you can say error comes in because it's a huge value. It's a really great value. If you try to calculate e to the power 2.4 multiplied 10 to the power 14, your calculator will blow out. It's a great number, so you'll see an error in the calculator that it can't calculate this huge number. So you'll write the answer the way it is in this form. Okay, and it will happen mostly in much of the calculations related to increase in number of accessible states. You will see in previous questions as well, the previous problems 4.1 and 4.2, maybe that thing happened there as well. So that's a huge number, and calculators can't calculate it easily, so you have to use some modern advanced calculators or softwares to calculate such a great number and see what it actually equals to. So that is not needed right now, and you can write it the way it is. For those questions in which the power is calculatable, you can calculate it actually and write the answer right away, but that's not needed here. That's the final answer, and we'll meet you in next one. Till then, take care and goodbye. Like, share, and subscribe.